Hello everyone, my name is Angela Ko. I'm an MS student here in the Building Science program, and today I'm presenting my research thesis, Beyond the Building, Defining the LCA of Landscape Architecture. Just as a recap, for embodied carbon, that's going to be considering the material impacts related to the material extraction, the production, construction, transportation, and end of life. So far, we've mostly been examining the LCA of buildings because, of course, they have a high embodied and operational carbon. However, if we are going to be considering the sustainability at a larger scale, we of course want to be considering the other elements of the built environment. So for example, when we're thinking of landscape architecture, we think it's inherently sustainable because the vegetation is going to be sequestering the carbon, it's going to be storing it, acting as a carbon sink. However, in reality, when we're examining the other parts of the built environment, especially looking at the hardscaping, so that's going to be the stairs, sidewalks, pavement, roads, and such, that's going to be a significant amount of materials that need to be considered because they will have a high embodied carbon. So therefore, having LCAs of embodied carbon for the landscape architecture is going to be very important. So, of course, we know LCA is impactful. However, the current materials and methods that we have could prove to be a bit tedious. So I learned this the hard way with my senior thesis in undergrad, where I conducted an LCA of the Worcester Hall courtyard. Having to look at each individual assembly proved to be a rather tedious task. So therefore, for this research, we wanted to propose a more efficient method to do this. We propose having an area normalized embodied carbon intensity, so therefore measuring pavement at the per square meter scale instead. So the objective of the study then is to quantify embodied carbon of landscape paving assemblies using a scalable LCA framework. In order to do so, we conducted an LCA for several different paving assembly types using 3 case study sites on the UC Berkeley campus. Then we applied these area normalized carbon intensities to calculate the total embodied carbon of pavement on campus. So, in order to do this, we wanted to see, this is our UC Berkeley campus. It's 178 acres in total, and there's a wide variety of the buildings, green space, and hardscaping on campus. So, just to put these into more so numbers, we can see the building footprint is a ground cover of 27%. Whereas for the landscaping on campus, that's including the green space, the roads, sidewalks, courtyards, that's going to be a total of 69%. So that's a lot of carbon that may not have ever been accounted for. I also want to note that the UC Berkeley campus is rather green compared to other urban contexts. So if we're looking at our cities, it's going to be way more hardscaping than this. So therefore, it's really important to be assessing these numbers. So we have 3 different UC Berkeley case sites that we had selected. This was based off of the construction recency as well as the larger variety of different paving assembly material types. So first we have the Haas Business School, then the newly constructed Grimes Engineering Center, and then the Lower Sproul Plaza, which you can actually see over the balcony here today. And I also just wanted to give a shout out to the several industry partners who I noticed were working on these projects. It was really cool to see all of your names on there. So from these different case studies, we had collected 25 total assemblies and categorized them into these 4 here. We have asphalt paving, concrete paving, brick pavers, and precast pavers. The asphalt paving is a rather simple construction of the asphalt on top of aggregate. For concrete paving, there's the unseen reinforcing steel that is going to contribute more to the embodied carbon. Then for brick and precast pavers, there's going to be the sand and mortar and such. And for precast, this is a more general category, including the stone as well as concrete here. So it has a larger variety of embodied carbon values. So then, with all of these, we were able to create these median embodied carbon area normalized intensities by the assembly types. So first, we have asphalt paving, which has the lowest of 7.7 kilograms CO2 equivalent per square meter. This is rather low, reflecting its simpler construction. Then we have concrete, brick, and precast pavers, which are grouped within a range of 45 to 55 kilograms of embodied carbon. And this is reflecting its more complex construction and material typologies. So with that, we have per square meter, what is the embodied carbon of these different paving assemblies. Then we wanted to see how is this going to apply for the embodied carbon of all of the paving on campus. This is a rather tedious task to do, so instead we utilize remote sensing in order to classify the paving material types. First, in order to do this, we sourced a high-resolution satellite imagery of the campus. After that, we built a training set from the known spectral signatures. For example, I'm confident that this road is asphalt. I'm confident that this courtyard is brick. Then, with that, we trained a random forest machine learning model to classify the pavement materials. So this machine learning model had an accuracy of 83%, so it required some validation and verification on our part in order to ensure that these were accurate. After that, we utilized the per square meter embodied carbon intensity with the areas of these material types, and we created this embodied carbon heat map of all of the pavement on campus. So just to blow this picture up a bit more for you all, we have these assembly types that we classified with our machine learning model. Asphalt paving is the leader at 56%. This is because we have it mostly within the roads, as well as a lot of the walkways and some courtyards even on campus. Then we have concrete paving, which is highly utilized, of course, in sidewalks. And then for brick and precast pavers, these were largely used within the courtyards and different plazas on campus. So here's our embodied carbon heat map again. This really just shows where the carbon is going to be concentrated on campus. This is largely going to be within a lot of the more popular aesthetic plaza areas, such as Lower Sproul Plaza itself, as well as the Campanile Esplanade. So lots of amazing places that Berkeley is known for. These also have the high embodied carbon though. So here are the actual numbers for the total embodied carbon at the campus scale. When we look here for asphalt paving, it has a median embodied carbon factor of 7.7, which is rather low. However, it's the leader of around 3,500 tons of carbon embodied within that. And this is just something that I want to note here. Of course, asphalt, it has such a low impact, but it's also not the prettiest material to be using. So we need to be thinking of these different synergies here of aesthetic versus sustainability. Additionally, then, the concrete paving is both high in the embodied carbon intensity, but also high in the area of usage. So that's a rather high impact there as well. All of this totals to 8,238 tons of embodied carbon for the UC Berkeley campus pavement. So I mentioned hardscaping. This is going to be thinking of stairs, ramps, and such. We only looked at the pavement, so at the 2D scale. So this number is actually going to be an underestimation of the total impacts that we have for landscaping and hardscaping on campus. So, of course, we think landscape architecture is sustainable, it's going to sequester all the carbon, and it will be okay. Just plant more trees. However, this is not the reality. Just for our 178-acre campus, the pavement hardscaping embodied impacts alone would require 8,300 acres of forest's annual carbon sequestration. That is around 46 UC Berkeley campuses in order to sequester that carbon. So plant more trees, not necessarily the answer. We should be examining other aspects of maybe the construction, or as Franco was mentioning earlier, we could also be thinking of the materials that we're using. So of course, no study is without its limitations. So for softscaping and vegetation, these were excluded from our system boundary. This is because when it comes to vegetation, there's very limited research on the actual quote-unquote embodied carbon and the amount of sequestration potential of the landscape architecture. So it would be exciting then to look more into, for example, biogenic versus fossil global warming potential. Lots of exciting work could be done there. Additionally, just want to reemphasize, this was an underestimation of the total embodied carbon for the hardscaping on campus because we were only looking at the 2D scale. And lastly, we did not account for the maintenance, for example, when asphalt needs to be repaved over time, or the climate resiliency impacts. There's a lot of synergies that could be seen between, for example, the urban heat island effect, stormwater management, and the embodied carbon. So that's another exciting path to look down. So the key takeaways here are that the campus pavement hardscaping is accounting for around 8,200 tons of embodied carbon on campus. This value has never been considered before within the campus sustainability plans or the net zero targets that UC Berkeley has set out for. So we've been operating more so on an incomplete picture here. And landscape architecture, therefore, must be included within embodied carbon accounting. We think vegetation will be the sequestering ability. However, in reality, it's going to be the sidewalks, the roads, the courtyards that are going to lead to a much more significant embodied impact. And therefore, this area normalized embodied carbon intensity framework could help support both the early stage design decisions as well as the larger scale campus planning operations. So I just want to show this image here at the top. UC Berkeley is currently undergoing a large redevelopment plan where they're going to be adding a lot more buildings as well as hardscaping and green space. And with that, this framework is going to provide the planners and designers an ability to quantify the carbon that we currently have, where the carbon's concentrated, and advise on the future decisions of how we're going to be designing this campus towards sustainability throughout the entire built environment. So with that, I'd also like to finish and say that I'm graduating this May. I'd like to give a shout out to my advisor, Matt Roberts, who has been here through it all since my undergraduate thesis even. And I also wanted to take the time to thank the industry partners. I had networked a lot in these meetings, and I'm really excited that through that, I was able to accept a position at PAE, which I'll be starting in this summer. So just wanted to thank the industry partners for that. And with that, before I conclude, I just want to invite you all to join the breakout session on the LCA of Landscape Architecture. We're going to have a lot more conversations, not just for landscaping, but also expanding to the other parts of the built environment and their embodied impacts. So now I'll open it to questions. Thank you.